You are welcome to the Onassis Lecture series, public lecture. Our very distinguished guest is Professor Barish from Caltech, one of the people who has a central role in detecting the gravitational waves. And he's honored by the Nobel Prize 2017 in physics. We are very happy for having him here and the other distinguished lecturers. Change now to Greek. Οι διαλέξεις Ονάση που διατηρήθηκαν στην πραγματικότητα το 2000 σε συνεργασία του Κοινοφελούς Ιδρύματος Ονάση και του Ιδρύματος Τεχνολογίας και Έρευνας έχουν ως σκοπό να προσελκύσουν τους πιο διάσημους, αναγνωρισμένους επιστήμονες από όλο τον κόσμο σε θέματα των φυσικών επιστημών και τους καλύτερους Έλληνες φοιτητές και όχι μόνο για μια σειρά εβδομαδιαίων διαλέξεων της διαλέξης Ονάση, όπως το ονομάζουμε σε συντομία. Είναι η 27η διοργάνωση που κάναμε τώρα. Ξεκινήσαμε το 2001 και κάποιος με ρώτησε πριν, στα 100 χρόνια θα είμαστε εδώ να τους έχουμε ακόμα να τις γιορτάσουμε. Μα λέω μακάρι να είναι έτσι, αλλά δεν ξέρουμε βέβαια πώς θα έρθει το μέλλον. Αλλά μέχρι σήμερα με την συμβολή τόσο του Ιδρύματος Ονάσης, του ΙΤΕ, ήμασταν σε θέση να έχουμε εξαιρετικούς, όπως σας είπα, ομιλητές. Ως τώρα είχαμε 22 κατόχους του βραβείου Νόμπελ, μεταξύ άλλων, και γενικά έξοχους επιστήμονες από όλο τον κόσμο. I would now invite the President of the Foundation for Research and Technology Fourth, Professor Nectarios Stavronakis, to address you.
Αξιότιμοι καλεσμένοι, φίλες και φίλοι, καλησπέρα. Εκ μέρους του Ιδρύματος Τεχνολογίας Έρευνας θέλω να σας καλωσορίσω στη δημόσια ομιλία του φετινού κύκλου επιστημονικών διαλέξεων με θέματα βαρυτικά κύματα που διοργανώνουν από κοινού το Ίδρυμα Ονάση και το ΙΤΕ. Θα συνεχίσω στα αγγλικά τώρα για τους διακεκριμένους επισκέπτες μας. Dear Professor Barish, distinguished guests, dear colleagues and friends, on behalf of the Foundation for Research and Technology, it is a great pleasure to welcome you all to this year's public Onassis lecture, focusing on gravitational waves. We are indeed delighted to be able to host the lectures again after a 3-year interruption due to the pandemic, as you know. Fourth, places special emphasis on advanced education and training activities for students and young researchers. The Onassis Lectures, which are supported and organized jointly by the Alexander Onassis Public Benefit Foundation and Fourth, nicely cater to this directive. Since the now long tradition began back in 2001, as was mentioned already by Lianis, they have become an important part of scientific life here at Fourth. I would like to thank our distinguished speaker for this evening, Professor Barish of the California Institute for Technology, a Nobel laureate in physics, for delivering the public lecture. I would also like to thank the eminent guest speakers for the exciting seminars all the week. In closing, I would also like to thank the Onassis Foundation for the continuing support, as well as Professor Lianis and all the members of the Onassis Lecture Committee for reviving the lecture series after a long hiatus. Thank you all for coming, and let's hear about the recent and exciting developments on gravitational waves.
I would like now ask the astrophysics colleague, Professor Nick Kilafis from the University of Crete, to introduce Dr. Barish. Good evening. It's a great pleasure and a great honor too to introduce today's speaker, Barish. Barry was born in the United States in 1936 and did his undergraduate and PhD studies at the University of California, Berkeley. He received his PhD in high energy experimental astrophysics, not high energy physics. I repeat, experimental high energy physics in 1962. And during those years, the experimental high energy physics was thriving. A year later, he went to Caltech on a postdoctoral appointment. But soon thereafter, they liked him so much that they offered him a faculty position and stayed there ever since. From 63 to now, so it will be 60 years next year. Impressive. While he was at Caltech and doing experimental high energy physics, he worked on and led several important high energy experiments. However, when the United States Congress decided to kill the superconducting super collider, the SSC as it was known then, he didn't know what to do, and he was thinking what to do. And while thinking, the Caltech officials asked him to take the lead of the LIGO project, that is the detector that was to discover the gravitational waves later on. So he became the leader of the LIGO collaboration in 1994, and 11 years later, the first detection of gravitational waves happened, 1995. For such a big event, no surprise, 2 years later, he won the Nobel Prize. We're very excited and honored that Barry accepted to be the main Onassis lecturer this year. We are all very lucky that we will hear about gravitational waves directly from the horse's mouth, as they say in the United States. Barry?
Hello, everyone. I'm happy to be here in Greece. I've been only here once before, almost as long as some of the history you heard about with my wife, who's in the first row, and it's nice to be back. It's also nice for us, in this case being myself and my fellow lecturers, to come here to participate in this distinguished lecture series that's run here. These lectures, this kind of lecture series, is really very important for young scientists. The idea is that more senior scientists run a school, very advanced school, not where we give grades or anything like an academic school, but exposing young people to what you've done, what we'd like to do, what maybe are the main problems in a field. Our field is so young, we haven't had the opportunity to do this before. So having a history in elementary particle physics, I had experienced these kind of schools quite a few times, and they've been very important in the development of especially young people in the field. And for us here in this week, we have a very inquisitive and active young students who are here for the week, and we're telling them what we know, what some of the problems are, and hoping that some of them will find a career in this area or something near that. So anyway, I assume that most of you came today to hear on a very accessible level a physics lecture. And I'm going to disappoint you by giving you a history lecture. So this lecture is going to be in the form of a history lecture where you'll understand maybe some of the lessons and how a science moves forward up until we detect gravitational waves. As I say, this is such a new field that I've chosen not to show you the highlights of what we've learned in only 4 or 5 years, which is the time since the discovery, because I think that most of the field is still in front of us, but rather talk about the history of what we know about gravity, how gravitational waves come into that picture, going back to the time of Newton. So tighten your seatbelts, and that's what we'll do. So first, this is the climax, and that is, this is the picture of the discovery of gravitational waves. I'll just point out a couple numbers in it. What you see is a panel on the top and a panel under it. The panel under it is the predictions of gravitational waves from Albert Einstein. And you can see, except for the weakly experimental data on the top panel, that I guess I have a pointer, that this is data and this is Einstein. And you can see they look alike. This is the first event seen in gravitational waves with confidence given because we see it twice. This is in 2 different detectors halfway across the United States, who both saw it at almost the identical time. The small difference in time tells us something about where it comes from. So that's the discovery. I'm only going to bring you up to that and just a little bit beyond that. And instead, we'll go back and start with what we know about gravity. And all of us learned something about gravity from the time we were young kids. Gravity has the particular history that arguably the most important physicist of all time, Sir Isaac Newton, spent much of his career trying to understand gravity. And then he wrote a book called the Principia, which in it gives his picture of gravity. That picture of gravity we all more or less have seen in school, and that is, if you have 2 objects that have some mass and they're near each other, they will attract each other, and the attraction will be proportional to the product of the mass of the 2 objects, and inversely proportional to the square of how far apart they are. So it's much stronger if they're close together. And he said it was multiplied by some constant that he couldn't determine, G. He did this in the Principia, and the important thing is that he didn't do this just in one special case, but he realized, or at least believed, that this was a universal truth, that it was true for objects like I show here. It's true for the moon going around the Earth, the force of that, the Earth around the sun, for understanding phenomena like the waves in the ocean, which are pulled by gravity, or anywhere else, like the apple falling out of the tree, that it's a universal truth, if you want, in science. And that's what we look for in science. We want the rules that describe nature, not just in a special case, but describe nature in a general way that we can apply to something new and different. And that was true for Newton's theory. Now, Newton put this forward in this beautiful book. There's 100 copies in the world, usually in a museum, called the Principia. In that same book, by the way, he wrote down what is called the scientific method, which is part of that same book. So it's a fantastic book. This theory, basically as formulated by Newton, lasted for more than 200 years without modification. The modification, which I'll talk about, is an illustration of how science changes. It isn't that Newton is wrong when I get to it. It's that he's incomplete. And we have a better description of gravity now. But let's take the steps. First, Newton gave us this formula, but he couldn't tell what this big G is. I'm not going to tell you the details of why it's so hard or how to conceive to do it, but it took 100 years before anyone figured out what this big G is, which is how strong the gravitational force is. That's the constant that's given. That was determined by, this is just the book, The Principia. That was determined by Henry Cavendish, an independent scientist who basically funded his own work because he came from a family of wealth. And he had attacked the problem of what is the weight of the Earth. It turns out, without going through the details, to understand what the weight, if you figure out what the Earth weighs, you actually are able, or you determine what this big G is in the formula that Newton has. It was done by what I show on the right in a more modern version, which is a torsion balance. The idea there is a vertical rod comes down and two horizontal rods with some weights on the end. If you twist that, it'll come back to where it was. And so what he did was twist it and see how it comes back. But then he brought up to it two big lead weights and saw how much it bent. This is a modern version because I show you one with a laser that can measure how much it bent. In his case, he didn't quite have lasers, but basically he determined this constant. This is the present day number for the constant. Forget the units exactly, but you can see it's known to many decimal points. Interestingly, after 100 years after Newton, when nobody could do this, when Cavendish did it, the answer that he got is better than 1%, is better as an accuracy within 1% of the present day best measurement of this constant. Anyway, the combination of Newton telling us how gravity works and then Cavendish helped us understand everything, as I said, all the way through the 1800s. It got a little rocky in the 1800s, and I'll describe that a little bit in words. In one thing that happened is whether, and we're doing that now, for example, I'm going to talk about Einstein's theory in a while, but one thing we do is try to test whether it's right or it has to be modified, just like we did with Newton, and that's the continual work of scientists or physicists. In the case of Newton's theory, it described everything, except that there was a puzzle in about 1820s. And that puzzle happened to do with the orbit of Uranus around, which you could calculate using Newton's equations. And the orbit of Uranus was just a little bit different than the calculations. And a French mathematician, astronomer, Leverrier, basically, instead of saying Newton was wrong, he basically said maybe there was something missing in the calculations of whether this orbit should be. Maybe there was another planet. So he, what we would call reverse engineered the problem. And he was able to say that he would fit the data of Uranus if there was a missing planet, and he could tell you where it was. He was a bit of a showman, so he actually wrote a letter to an astronomer in Berlin. He was in Paris, and told him where to look in the sky and when. And within 1 degree, he saw the planet Neptune. So the discovery of the planet Neptune, it was based on us believing this universal theory and then applying it. And then seeing that somewhere that looked like it didn't work meant you didn't know everything about the problem that you were working on. So science keeps advancing. Newton's theory is still 100% right. Later, about 20 years later, in the 1850s, a new problem developed, not even as big as that one, and that is the planet Mercury. So we had one more puzzle that came. The planet Mercury, I'll remind you, is the planet closest to the sun, and it has a very elliptical orbit. It goes way out and comes back under the sun, and I've kind of drawn it here. And you can calculate from the gravitational fields of all the planets and so forth where it'll go each time, and it goes around a little bit like a flower, a daisy, and you can calculate then how much it should move. And the answer is close using Newton's theory, but again, didn't work. So I give the numbers here. Basically, Newton calculated that in a century, it would move forward 532, the units are arc seconds. And actually what was observed was about 10% more than that. And so that was a puzzle. Leverrier, the one who discovered Neptune, then reverse engineered it again and believed that there must be something between Mercury and the sun. And in fact, he predicted there would be a planet between Mercury and the sun, or some masses between Mercury and the sun. He even gave it a name, which is in a different form in a popular television series called Vulcan. So the planet Vulcan was looked for between Mercury and the sun, but for the rest of the 19th century. So by the time Einstein came along, which was the beginning of the last century, this puzzle was the only one that still existed that didn't fit Newton's theories exactly. So after more than 200 years, this was the sole discrepancy in Newton's theory, and it's only a 10% effect. And maybe the experiments looking, there were false discoveries, by the way, but I'll skip those. Maybe some of the, maybe there's still something between Mercury and the sun. And in fact, well after Einstein, NASA had a series of satellite observations looking for something between Mercury and the sun, and they didn't find anything, down to something like 10 kilometers in size. So anyway, this was the only puzzle that existed by the time Einstein came. It's unlikely, but we don't know exactly, that this is really what drove Einstein to develop a different theory of gravity. But there are other questions that exist, what I would call incompleteness in Newton's theory, that would stimulate having another theory. And let me grapple with those a little bit. Einstein then introduced a new theory. This was in 1915. He had done 4 what were phenomenal theoretical papers in 1905. And most physicists celebrate Einstein's magic year in 1905. There was a big celebration in 2005 of the 100th anniversary of Einstein's 1905. He did these very quickly, and that's why I mentioned them. 4 problems that no one else had solved. And then it took him 10 years because the mathematics was hard, but his perseverance was there to come up with what he calls general relativity, but it's his theory of gravity. In a sense, it was taking relativity, which existed in 1905, and it talks about when velocities go near the speed of light, and put in accelerations. So not just velocities, but changes in velocity, which is acceleration, and that's gravity. So Einstein did that, and he came up with something that basically has a totally different idea, and that is that gravity isn't a force like Newton said, but actually it's something that's built into the structures of space and time itself. And that space and time, by the presence of any massive object, are distorted or curved. And nothing can avoid feeling this curved structure because it's the structure we live in. And that's what makes gravity itself and what makes it universal in words, let's say. I'll come back to that. But the first victory, you'd say, is that Einstein, in his formulation, and this was in his initial talk when he introduced the theory, was that he got the right answer, or let's say the answer that people measure for the orbit of Mercury around the sun. So if you include the kinds of curvature in space and time, which I'm not going to talk about mathematically, that Einstein does, it got the right answer for this. That's hardly the reason to throw away a theory that's 200 years old and start a new one. Usually we believe that you have to predict something new. I'll come back to that. But in fact, when we reflect on Newton's theory, there's reasons to know, and even he knew some of this, that it couldn't be complete. The first thing that I'll mention is that imagine that the sun burned out right now. We wouldn't know it on Earth for 8 minutes, which is the time it takes light to get from the sun to us. So what that means is gravity, or any force that we have, travels at some speed. The speed of light is the fastest speed that we know, but it's finite. And so the problem, and this is actually mentioned in the Principia, is that Newton's theory has instantaneous action at a distance. So what does that mean? That means when the apple falls, you see it right away. There isn't some time for the message to get from the apple falling to you. That doesn't bother most things that we did with Newton's theory, but he realized that that was missing somehow, that the idea that it takes some finite time for a message to get to you was something that he didn't grapple with. He didn't deal with it, he just mentioned it. The second thing that's maybe conceptual is that Newton's theory, and this to me is embarrassing for myself, and I think for probably almost any of us, when we were young kids and we went to school, our teacher told us if we jump up, the earth pulls us down. And fine, I believed that. But in fact, the logical thing for a curious kid to ask is, why does it pull us down? Why don't we keep going up? So what makes the force of gravity attractive and not repulsive, for example? And that's not explained by Newton's theory at all. So the fact that he wrote a formula that's attractive, he just assumed it was attractive, but we don't know an underlying reason for it to be attractive. Einstein gives us that. In Einstein's theory, the message is transmitted at a finite speed. That was the speed of light. And the reason that objects fall toward each other has to do with the distortion of space and time that I talked about. So in this little cartoon you see here, you see what happens when you, in a kind of two-dimensional picture, you see what happens in Einstein's idea when there's a massive object. What's shown here is the Earth, and you put it on a grid. Think of a trampoline. It would distort it as shown here. And then if you put a marble or something, the moon or something on this same grid, it's going to roll or want to roll toward the center. So the attractive force is due, in Einstein's theory, to the distortion of space and time. So Einstein's theory immediately solved two conceptual problems, I would call them, with Newton's theory, and one being instantaneous action at a distance. So in this case, the message travels at the speed of light. And the second being why the force is attractive. So both of those are solved by Einstein. And the third one was the only puzzle that existed in that day, was the puzzle of why the message gets transmitted in Einstein's case. So now, generally, that's great. So it's conceptual and all this that I told you, but that isn't why we would move on to a new theory after more than 200 years. So the first thing that, and Einstein realized that, so he immediately had, from the very beginning in his first seminars, predicted something new. And the something new was conceptually the picture like I showed, the grid shown here, where you can see the sun, you can see the earth, and you can imagine that anything that passes near the sun is going to be distorted by the grid that I show below that's just distorted. In fact, it won't matter whether the object that is moving in Einstein's theory has mass, like Newton would require, or it's massless, has no mass. So Einstein, in his theory of gravity, predicted that even light would be affected by the curvature of space and time. And in fact, he went the next step and made a prediction of how strong it would be and how to test it. And that is to look at the sun, like I'm showing here, at the time of an eclipse when it's dark, and watch while it's dark for the couple of minutes. Any stars move behind it, and the trajectory from the star, the light from the star will bend as it comes around the sun. And that was actually tested in 1919, and it was proven to be not only bending, but bending at the same amount that Einstein had predicted, and that was done by Sir Arthur Eddington. I think I'll show you that in a minute. One way to think about the whole problem is that Einstein's equations have kind of an analog in materials. When we think of materials, people wonder when you say space and time are distorted, why they're not big effects and so forth. It's true for materials. We have materials that are very soft and you can bend them a lot, or ones that are very stiff. And probably fortunate for all of us, if we think of space and time and Einstein's theory of relativity, how much it gets distorted, the numbers are that it's very stiff. It's like a very stiff material. Things don't get bent very much. And so the effects are very small. Maybe that's lucky. So for most of life, we're not affected by this curvature of space and time. But in fact, light doesn't go exactly in a straight line like we think it does if it goes near a massive object. So you can imagine the bending of light itself, the prediction of the bending of light was a pretty astounding thing. And Einstein made that prediction in 1915. It was measured in 1919, and then again a couple times later in the early 20s. This is interesting to me. It's the New York Times headline at the time that it was reported that the bending of light was seen. And you can see that the reporters that wrote the newspaper thought this is a bunch of crazy scientists. It talks about lights all askew in the heavens. Each sentence is basically the craziness of scientists that talk about the bending of light. But in fact, it was this discovery of the bending of light that actually made Einstein a household name. For us in physics, it was 1905. And when he solved several problems, and maybe those of us that work in this area take 1915, but what made Einstein a household name was the discovery of the bending of light, which was then announced all over the world. And now another kind of lesson of physics is the bending of light. And this happens often in physics. We make a discovery, and then that discovery provides for us tools to make more discoveries or more understanding in nature. And in modern astronomy, actually, the bending of light is used quite a lot in what we call gravitational lensing. And this is looking at an object and studying it or something behind it by the fact that light going around an object, like I showed you for the light going around the sun, is bent. And this is a picture of light going around an object. The most dramatic one that people see with not quite the naked eye, or it's hard to with the naked eye, but usually in the Southern Hemisphere is called the Einstein Cross. And it has this unique feature because of the particular kind of effects that it's imaging. Anyway, all of this new theory of gravity and so forth might seem rather abstract. And especially for the general public, why should you care about any of this that I've said? And I'll tell you why. Because when we learn things in science like this, often, but not necessarily immediately, it has a great practical application in us understanding something that we care about in nature. An example from my own experience, as was introduced, coming from Berkeley, was the discovery when I was a student in Berkeley, not by me, but by people in Berkeley and other places, of another idea of Einstein's called stimulated emission. Nobody had any idea that could be of any use. It was just a physics thing that people got a Nobel Prize for and so forth. But 10 or 15 years later, people realized that this particular stimulated emission had a focusing of light. And now it's a $20 or $30 billion industry. It's the modern laser. So the laser that we use for so many things is there because we made a fundamental discovery in physics. In terms of Einstein's general relativity, there's a practical use that we couldn't do without that theory, and that is GPS, global position monitor, that tells us where we are and enables us to guide our car or ourselves down a road. That's done by having a set of satellites. And the satellites, we measure the relative time it takes a signal to go back and forth to the different satellites. It was originally developed by the Air Force in the US, and they knew enough to take into account the first discovery of Einstein, the theory of special relativity, E equals mc squared. And that is, we learn when we study relativity as a physics student that moving clocks, that is, if you have a clock that's moving very fast, it ticks more slowly, doesn't tick at the same speed. And so basically, the fact that the satellites are going something like 14,000 kilometers an hour as they're going around the Earth, that's relativistic somewhat. And so you have to make a correction. So inside the satellites, they actually make a correction for the light going back and forth, and it's 7 microseconds a day. But there's a second correction, and that comes from this theory that I'm talking about today, general relativity. And that comes about because where the satellites are, there's only about a quarter as much gravitational field as there is on the Earth's surface. It's somewhat higher. And so if you use general relativity to calculate, you find that clocks, in this case, clocks go faster, and it's actually a bigger correction than special relativity. If you make these corrections, then you can keep yourself on the road. If you don't, you can ask yourself how long you would stay on the road. And if you put in the numbers, it's about, and a road was about 10 meters, which is pretty wide. Across, it's a couple minutes. In a couple minutes, you'll lose the position you're in. So anyway, let's move on. So Einstein then had introduced general relativity. The next step he made, and the one that affects the rest of my story today, is that the year after he introduced general relativity in 1916, he then introduced the idea that maybe gravity, like electromagnetism, has waves. And of course, that's what we're going to end up with today. And he published a very short paper in 1916 in German, which I have here. That paper actually doesn't have even very much derivations or formulas. He didn't and wasn't able to derive the fact that that gravity would have gravitational waves, but he looked and noticed similarities between the formulas of gravity, as in his theory, and electromagnetism, which does have waves, the lights, radio waves, microwaves, and so forth, and made the leap, which is Einstein, that if electromagnetism has waves, gravity must also have waves. And he made the arguments why that would be true, but not the derivation from general relativity. That initial paper wasn't perfect. It had a couple of errors, including the strength of gravitational waves, which he fixed in a paper 2 years later in 1918. And in the 1918 paper, he also told us what would make gravitational waves. And electromagnetic waves, which we're familiar with everywhere, were discovered in the 1880s by a physicist named Hertz. And what he did, just in simple words, is he took two charges and he oscillated them like this. And when he oscillated them, they made electromagnetic waves. A dipole, we call it, a two-pole, and it made electromagnetic waves. He went in the next room and made a receiver that could detect the electromagnetic waves. He detected them. And then he moved forward and backward to see if they acted like a wave that would go up and down. And they did. And that was the discovery of electromagnetic waves. Now, basically, Einstein says in 1916 and then in 1918 that there must be also gravitational waves. I'll show you later that we can't quite do what Hertz did in his experiment. So Einstein's 1918 paper basically tells you how to make gravitational waves. And instead of something that's what we call a dipole, that's just a charge going back and forth, it really has 4 poles. It's what we call a quadrupole. And so we need something that makes this kind of form. And an example of that is 2 objects going around each other, like the moon around the earth around the sun. Or in our case, it's going to be 2 black holes going around each other. And that makes this so-called quadrupole moment. There's other ways of making it, but that's basically a way to make this. And what happens then if I have 2 objects going around each other is that in this idea of Einstein's, it'll make gravitational waves like electromagnetic waves. They'll travel outward at, again, the speed of light. And they'll travel outward in this theory with nothing but distorting space and time. Electromagnetic waves, when they travel, have an object connected to them, which we call the photon, which carries the electromagnetic waves. And Einstein's theory of general relativity is truly a ripple in space and time itself. A little bit like throwing a stone in a pond. The stone sinks to the bottom, but in the top, the ripples that go are just in the water itself that go outward from when the stone went in the water. So there's no object that goes with it in Einstein's theory. One thing that we try to test, in our case, measuring gravitational waves, is whether there's some sort of object connected to it, which we call a graviton. And we talked about it some in this week's lectures. Okay, technically you make gravitational waves by an object going around each other. I show it here, but I'm not going to talk about it because I'm going slowly. But basically, this system of going around, I can calculate quite completely. And it is the system, and the reason I emphasize it, that happened to be the system we used to make the first detections of gravitational waves. That it is, what I'll come to, is 2 black holes going around each other. When they go around each other, like the picture here, then the outward waves show as something going up and down in this radiate outwards and basically at the speed of light. So let's move on. The only formula that I'll show today, I show here is a simplified, you don't have to read the stuff on the left, is a simple, it just tells how I did that. This is a simplified form of Einstein's gravitational waves. And I write it down for people who are familiar with the form of electromagnetic waves, because this is more or less what Einstein recognized in 1916, that the form looks similar. The letters are different. This little h with sub mu and nu is what we measure in our experiments in gravitational waves. But the form of this is the same form that exists for electromagnetic waves, which then propagate through space in waves that we know, from radio waves to microwaves to all the other frequencies of regular waves. There's one difference, which I'll mention, and that is in the case of electromagnetic waves, there's 2 what we call polarizations, directions of the waves themselves, which can be separated, and they're perpendicular to each other. And in the case of gravitational waves, there's 2 components also, but they're at 45 degrees from each other. That's a technicality. And this is something we haven't yet measured. So it shows you that in this young field, we haven't yet shown that there's 2 components, although we believe it. We even know how to measure it, but our instruments aren't quite good enough yet. Again, kind of showing you how science develops. Einstein had not derived gravitational waves in 1916 and 1918, and then he more or less dropped the problem for 20 years. He immigrated to the US in 1932, and with him as his assistant or junior person was Nathan Rosen at Princeton University in the 1930s. They solved some really important problems in quantum mechanics and other things in the 1930s. But they also returned to the problem of gravitational waves with their goal as theoretical physicists to be able to calculate them from the fundamentals of general relativity. They tried to do that and they failed. And when they failed, they did calculations that gave infinities. This is a kind of disease of trying to calculate things that are hard and not doing it quite right in general relativity. And so they got what I would call cold feet, or got maybe a little dubious about whether their projection of gravitational waves was right or not right. And so they wrote an article. And the article is a funny one to write 20 years after they predicted that gravitational waves exist. They published an article, they wrote an article that said, "Do gravitational waves exist?" A rather funny title. They submitted it to our most prestigious journal in the US, which is Physical Review or Physical Review Letters. The editor at that time was a young man. I've got a picture of him as a young man. He was editor for many years, named John Tate. And at that time, and I don't know this history as well as I wish I did, but at that time, the editor had tremendous power in a journal. Articles were submitted, and then he had the ability to just accept it, reject it, or send it out to experts to review it. That's what we call peer review. I don't know exactly when peer review started. And I don't know when Einstein might or might not have experienced peer review because he came from Germany just a few years before, and peer review was just new in the US in the early 1930s. But at this time, because it may affect what I show you next, at this time, you can go back because it's been more than 50 years since that time and look at the book that has the records of the publications of the Physical Review. I was president of the American Physical Society, so we were able to go back and look at these. And this just shows a few examples, the second one being Einstein and Rosen, where this is Tate's logbook, where one of them he just accepted, one of them he rejected. He sent this one out for review. He sent it out to a reviewer named John Percy Robertson. And John Percy Robertson was actually a professor at Princeton University, where Einstein now was. And he happened to be at that time when this was reviewed on sabbatical at my institution at Caltech in Pasadena. So the article was sent to him and he reviewed it. And he noticed that the way they set it up, they got what are called coordinate singularities. And he showed how it could be done or hinted at how it could be done in cylindrical coordinates, and sent back his review to the Physical Review, to John Tate at the Physical Review. And Tate then sent a rather mild letter, because we have it, not the same kind of letter that probably most of us have gotten that rejects something we submit, that basically just asked for Einstein's reaction to the referee comments. Einstein didn't react very well to this. He basically, and Einstein then not only responded poorly, as my little cartoon shows, but he wrote a letter back to Physical Review saying that we, Mr. Rosen and I, had sent you our manuscript for publication and had not authorized you to show it to specialists before it's printed, which is probably what was done before peer review. I see no reason to address the blah, 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 in any case, erroneous comments of your anonymous expert. And on the basis of this incident, I prefer to publish the paper elsewhere. And in fact, as I'll show you, they did publish it elsewhere. And in fact, Einstein never published in the main American journals, American Physical Society journals, ever again before he died. So this is between the 1930s and 1950s. So Einstein at that point had an assistant. Rosen had left Princeton, and his assistant was another prominent astrophysicist named Infeld. And Infeld and Robertson, the one who reviewed it, knew each other well. And when Robertson returned to Princeton, this part of the story is not documented, but it's inferred. So everything I've said so far is documented. But as far as we know, that Infeld and Robertson talked, and Robertson basically pointed out how you could do this problem in cylindrical coordinates and not have these infinities. And in fact, he never talked to Einstein, we think, but then Infeld and Einstein rewrote their paper and they did publish it. And the publication had a final title that didn't say, do gravitational waves exist? It says on gravitational waves. The first sentence says something about the rigorous solution for cylindrical coordinates, blah, blah, blah. Anyway, Einstein never came back to the problem again. It still really wasn't accepted by the community of physicists, theoretical physicists. And in fact, it never was until after Einstein died. Usually, we attribute a particular point in history to when theoretically people believed that gravitational waves should exist. And that was a meeting in Chapel Hill, North Carolina in 1957. It was organized by a husband and wife who were general relativists, Bryce and Cecile DeWitt. And they had something like 40 leading theorists at this meeting. And at that meeting, the very first speaker was a British theoretical physicist named Pirani. And he made a very elegant proof from the fundamentals of general relativity that demonstrated that gravitational waves come out of general relativity. And that went a long ways to convince people at this meeting that gravitational waves must exist, because these were theorists and they believed that if you could derive it out of the theory, then it would exist. At the same meeting was Richard Feynman, my colleague for many years at Caltech, and he brought up another point. And his point was more a physical one. So if whether they exist or not, it doesn't matter if they can't do anything. So they must have to do something for us to believe that gravitational waves are relevant to describing physics describing nature, describing then gravitational waves. And he then made an argument which he called the sticky bead argument. And that argument I show in this little picture here, and that is you have a bar, and on the bar you put a couple of rings. And if a gravitational wave comes through, it distorts space such that the bar gets fatter and thinner down, depending on the wavelength down it. And that forces these rings to go oscillate on top. And that force, or that movement of the rings, happens because of what? Because of friction. Friction is the transfer of energy. So basically, if you can transfer energy, then gravitational waves have actually done something. So the combination of Pirani deriving gravitational waves and Feynman giving this physical argument basically is considered by most people in this field as the turning point where the problem changed from a problem that was a theoretical problem, does it exist, to one of how do you detect them and see what they're like in nature and study them. And so the first person to try that was also at this meeting. And in some sense, I think what he chose to do looked a lot like Feynman's suggestion. And that is take a great big bar. If I take a great big bar of very pure aluminum and hit it with a hammer, it rings at some frequency. And so he put these very sensitive detectors around it so that if a gravitational wave came through, then they would be detected by the swelling or the changing in shape of the big aluminum bar. And this was the first attempt to detect gravitational waves. And basically, he called it a resonant bar. It's resonant because it has a frequency that it likes. If you go up and hit a bell, or you hit a bar, it's going to ring at a certain frequency. And so these are the bars. This was then in various evolutions used as the main technique that searched for gravitational waves until we came to the technique that I'll describe in a few minutes, which is interferometers. This technique has a weakness, and that is that I can't decide, or if nature happens to have something that emits gravitational waves, they're not necessarily, or not likely either, to be at the exact frequency that this bell or bar wants to ring. So the fact is that this technique is a limitation, that it picks a particular frequency, and even if you can make it very sensitive, that may not be where gravitational waves are emitting signals. Anyway, that technique got better and better because experimental physicists like myself are pretty good at making things better and better and better. It got better by improving the electronics and pickups. It got better by what you see here, making them sealed and cooled to low temperatures where there was less motion. Got better by isolating it from the ground better, and so forth and so on. And even got better by making it somewhat broader in its frequency acceptance and compared to just the ringing of the bar. So anyway, so this technique was what was done. Unfortunately for the history of this field, and I'm not going to dwell on those, there was a couple claimed false discoveries, just like there was on describing, the orbit of Mercury, as I said, in the 1800s. And physics is strewn with those. We basically have ways that we finally determine what's true or not true, and all results we share with each other, and sometimes they're proven to be untrue. Anyway, this was the technique that existed until another technique was developed, which I'll describe next. I'm going to concentrate on one of many ways that gravitational waves could be made because it's the one that we happen to be able to detect and have used to discover gravitational waves. And that is the merger of two objects that are trapped by gravity going around each other. And then because they emit gravitational waves, they lose some energy and move in toward each other and eventually collide. The discovery that we made, the first one, was two objects going around each other that are black holes. I'll come to that. But basically, if I have two objects that go around each other, I expect them to give some sort of signal, as shown on the left. This is a hand-drawn figure that was actually drawn by my colleague Kip Thorne before we knew very much about what it would look like. And at the beginning, you can pretty well calculate how it's going to get faster and faster frequency and a bigger signal in the very left part. The rest of it is much harder to calculate, and so it's shown here in just in a notional way, and that is eventually they're going to come together and merge, and finally they have to settle down in some way. For describing the experimental situation, the picture on the right is important because what it shows you is that if these two objects are very light, they're going to make a different pattern and go to a higher frequency, we call it, than if they're very heavy. So I show three examples here where they get heavier and heavier. It's those differences in the end that enable us to actually, after we've detected something, to be able to tell what its features are. So that's an important ingredient, but it also tells you what you're able to detect and what you're not able to detect. So how do we detect gravitational waves? Basically, if we now put in the numbers because we know what the constants are in gravity, we know the strengths, we know what the gravitational wave strength is going to be, then I'm not doing it for you, but we can calculate the numbers. If you visualize a ring of say a meter diameter ring with free masses on it, around it, like I've drawn here, of radius L, then it turns out that in the one formula that I showed you, the little h is the amplitude of the gravitational wave signal. And for something like the black holes that I talked about, or maybe neutron stars, which we've detected, that number is tremendously small. And that's what makes both general relativity not distort the distortion of the space around us very much, but it also makes the gravitational wave signal itself very small and very difficult to detect. So the magnitude of what we expect that we're trying to measure is a small number. It's 21 zeros and a 1, 10 to the minus 21, an almost inconceivably small number. And we change that then if a gravitational wave goes through it, we'll change the distance so that the circle becomes somewhat of an ellipse, and the amount that it becomes an ellipse is just 1 part in 10 to the 21, or in this case, if it was a meter in size, where we have to see this little distortion of 10 to the minus 21 meters. That's a very small number to measure, as you might guess. And so it's the underlying reason why we make the detectors that I'll show you pictures of very large. We make them kilometers instead of a meter, so that this very small number, 10 to the minus 21, becomes a number more like 10 to the minus 18. A still very, very small number, but it's the first way that we do things. So I'm going to cheat a little bit by just saying that there's more, and my experimental colleagues, have their favorite part. But if I had to characterize what were the biggest problems that you had to solve to detect gravitational waves, and how well did you have to do it in the most simplified way I can tell the story, then I'd say you have to do this interferometry that we're doing, which I'll describe. Interferometry is this picture here. The laser beam comes in from the left, comes into the center. You divide the beam, send half of it vertically, half of it horizontally. If the length to the mirrors that are on the outside, which now are kilometers away, are equal distant, then the lights will bounce back and come back at exactly the same time. And those two beams, if you want to reverse them, cancel each other. So basically, and that's how interferometry works, whether it's our scale or any other scale. And if the phase difference is small, then you can measure to however good your optics are. Typically, if you go into a laboratory in a university where physics students measure an interferometer, they do something where they see what we call fringes, and they probably measure this delta L to 1 part in 100 or something like that in seeing the fringes, if they're lucky and do it right. And a good interferometer that you might find in a laboratory or be able to commercially buy is several orders of magnitude better than that. But the problem for us goes well beyond that. Our ability has to be able to tell the difference in the phase of these two beams of light to 1 part in 10 to the 12th. I can't do justice, and I won't do anything, to all the innovations that takes in doing interferometry. But the interferometry we do is basically based on somehow doing enough advanced techniques in interferometry itself to tell the difference to 1 part in 10 to the 12th. The second problem that I think is the major problem that we have is that we're doing this here on the Earth, in our case, in 2 locations in the US. And in those 2 locations, or anywhere on the Earth vibrates a lot. And we can't tolerate that in these instruments. And so we have to isolate them from the Earth. We do that with, again, a series of techniques, which I won't go through, which involve a fair amount of sophistication. And we start with something that's as simple as the shock absorbers in your car, which keeps your car from bouncing when you go down the road, which maybe gets you a factor of 10 or 100 or something going the road, but we have to isolate ourselves to 1 part roughly in 10 to the 12th. So isolating ourselves from the Earth was the second big experimental problem. I'm not going to go through those in any detail now because it was just to give you an illustration of why we took so long and worked so hard to do this. I just want to give you a feeling, just to remind you of how small 10 to the minus 18 meters is, what we're trying to measure. So we all know what a meter stick is. It's that long. A human hair, I don't have many left, are about 100 microns in size. That's 1/10,000th of the meter. A wavelength of light, like the light that's in this laser beam that I'm using here somewhere, is about a micron typically. And so that's another factor of 100 smaller. The atomic diameter brings us down to 10 to the minus 10 meters. Remember, we have to get down to 10 to the minus 18 meters. So we're talking now about if we're able to do things the size of an atom, we're still 8 zeros away, 8 orders of magnitude away from what you have to do to detect gravitational waves. So atomic sizes are 10 to the minus 10 meters. The size of a proton, the object that's used, say at the CERN accelerator to go around and study all these particles that come out, is 10 to the minus 15 meters. And we, making this big instrument, have to do roughly 10 to the minus 18. So we have to work and find things, differences in distance, that are about 1/1000th the size of a proton. Maybe that makes you disbelieve the rest of the talk, but that's what we've been able to do, and that's the sensitivity that we have. In fact, maybe even a factor of 10 better than that now. This shows the technique in a movie. And that is, the light goes to the mirror in the middle, goes down the 2 arms. If it comes back at the same time, this is shown with waves like what the real interferometer would have. The light goes down and hits a mirror. Same time the other mirror, they should come back at exactly the same time. If they do, you can orient it so they each cancel each other. One goes up when the other one goes down. And my detector, which is over here, sees nothing. But if they get slightly different from each other, and as I say, it only has to be different to 1 part in 10 to the 12, then we get some light on the detector. And that's basically, in the simplest terms, the idea of the interferometers that we use. The actual application, just to give you a sense, are these big instruments. This is the 2 in the US. There's one in Italy as well. The 2 in the US are one in the state of Washington, one in the state of Louisiana. And you can see the long arms, which have to be under vacuum, high vacuum. And they're 4 kilometers long each. And those are the 2 instruments that I showed you, made the detection that I showed. And this is just what the inside looks like. Big tanks that hold the mirrors, and everything is under high vacuum. So now the detection, and then we'll be almost done with our story. On September 14th, 2015, what we saw early in the morning in the US was the observation of a gravitational wave in both detectors. I showed you that on the very, very first introductory slide. Looking at when it arrived in those 2 detectors, where we were able to tell where it came from in direction, as well as this picture here. It basically came up through the southern hemisphere, came through Louisiana, and then Hanford, Washington, a few milliseconds later. And that basically was the first event, in that after it came through entered the Earth, about 20 milliseconds later, it entered Livingston, Louisiana, where our first detector was, and registered this data here, which is 0.2 of a second on the horizontal axis, and the famous 10 to the minus 21 on the vertical axis. So you can see these wiggles. Even the biggest one gets up to maybe 10 to the minus 21. So that's the size we have to measure. Then 7 milliseconds later, almost identical signal we saw in Hanford, Washington. It was seeing both of these that gave us confidence almost right away. Of course, we had to do a lot of work first to prove that we weren't fooling ourselves. They gave us confidence that we had seen gravitational waves, and we could fit that. I drew the lines through here. It almost did nothing because it fits so well to Einstein's theory. And so almost immediately, we were able to identify that it was 2 black holes merging and emitting gravitational waves at that instant. This was then the data that was used and published to give that event, and we got an award for doing that, as you saw. So, by the way, this is my 2 colleagues in the middle top. and my wife who's down here on the left. Anyway, more recent, the second real big discovery that we've made, and it's the last physics that I'll show, but it's still historical, which was in 2017, 2 years later. We basically saw a signal from something that it was different from before. It gave you a signal that wasn't 0.2 of a second, but tens of seconds or 100 seconds. By doing that, from what I showed you before, it meant they were much lighter objects. They weren't black holes. They were what we call neutron stars. And these two neutron stars made a signal with us. Neutron stars have the feature that, not being black holes, they can have science that can be seen by other kinds of detectors. They can emit particles, they can emit light. So in this case, what we fortunately had happen is that what's shown here on the horizontal scale, on the very bottom, is our signal. So our signal is here, and it happened at this time. Something like 2 seconds later, 1.7 seconds later, the same signal was seen by satellite of high energy photons in the same region of the sky. This shows their region of the sky, and this is ours. And so we were seeing that. Knowing that, we had the confidence that we had seen something. It was seen in high energy gamma rays. And so the whole astronomical community was alerted. And being alerted, basically measurements were made in something like 2,000 instruments out of the 4,000 or so that are around the world. I think the biggest mobilization in astronomy ever. And basically, it enabled measuring the radiation from this in different wavelengths as a function of time. That turned out to fit various models and maybe describes, and this is again more or less a lesson in how physics works, describes something that you weren't even aiming to do. So we're trying to study gravitational waves. We're studying, in this case, something that is very exciting for us because it is studying what we now call multi-messenger astronomy, seeing something that in gravitational waves, in telescopes, and maybe something like neutrinos at the same time. But there's a piece of physics that may be true. We never know when we only see 1 or 2 events. But I remember as a student being presented with a problem that we should all, kind of know, you'd think, and that is, many of you in the audience have a ring on your finger made out of gold or platinum. Do you know that we never, as physicists, have been able to explain how, when the Earth was formed, gold, heavy metals have gotten into the Earth, like gold and platinum? In fact, the idea always is that if we explain it, is the universe is primarily made out of hydrogen and helium. That's the lightest elements. And we have stars that were formed, and stars actually have a way that they burn and make the light and energy. It's actually the fusion process. And that's been proven. And the fusion process actually burns up the light elements, hydrogen, helium, lithium, oxygen. But once it gets up to iron, it doesn't work anymore. So we have not a very good way to explain how heavy elements got into the Earth when the Earth was formed. We know how they're made in the lab because this goes up to much higher numbers, you can see on the plot here, than iron. And in the lab, we tend to do experiments where we bombard neutrons on a heavy element and make heavier ones. And that was popular even as far back as the 1930s. It was what Enrico Fermi was doing. So basically, in this case, when we saw the collision of 2 neutron stars, the models that tend to fit the data, and we never really know until we get much more data, were called some sort of merger theories, which basically have a nuclear physics description where you can calculate things. And so basically, if you take the calculations of a simple model like this, that particular neutron star merger that we saw actually created 100 Earth masses of gold. Now, of course, it happened now. It didn't go into the Earth. But the idea is that earlier in time, maybe these kinds of neutron star mergers were what created the heavy elements that are now in the Earth. So to me, this is an illustration how physics is very interrelated. We work on one problem, but maybe it gives us insight into something that's quite different than that. I just want to point out this field is just beginning. And some of us, we're talking about it this week and the next 2 days especially, are looking at what we do with the next generation of such detectors. And there's proposals to do this, but I just wanted to mention a couple of the technical things. You can make them bigger, that'll make them more sensitive. You can make them with, by cooling them down to lower temperatures, that turns out to make them quieter than they would be otherwise. And we want to distribute them so that we can do more science where you see both electromagnetic signals in telescopes, maybe neutrino signals, and gravitational wave signals at the same time. And probably the ultimate goal right now, and what we understand, is to try to use gravitational waves to understand signals from the earliest times in the universe. We now have a problem that the best tools that we have to study the early universe is photons, like for everything else. But the trouble is the early universe itself was so dense and opaque that we can only look back to 400,000 years after the Big Bang. So trying to understand the first instance of the universe, or something that we believe or infer called inflation, requires going back to even earlier times. And it might be, not today, but in the future, that we can go back to earlier times. First, the possibilities are neutrinos, which don't get absorbed so much like photons. And they could go back to a few seconds after the Big Bang when particles were interacting and making each other. That's very difficult because the neutrinos turns out technically are very low in energy. And maybe we can have gravitational waves that we can detect from the early universe. So that's something we don't know how to do today unless they're different than we think. And it just gives you an idea. So basically, I've given you a little history, and we're in the first instance, I think, of the birth of a new field of astronomy. Thank you.
Thank you really very much for your excited talk. May I have the possibility for a few questions? Only a few questions.
Thank you. Can you hear me? Yes. Thank you very much for this very interesting talk. History lesson, as you said. What is the fraction of the events that we can detect based on our technology? In other words, how many events are we missing that we could potentially detect? And would we detect more events if we could put an interferometer in space, let's say? Thank you.
So if I understood the question, it had to do with how many events and what limits us and what we have. We presently, I showed you two. We presently have just about 100 examples of gravitational waves. So we have 100 events. This is 5 years after the first detection of gravitational waves. The kind of detectors that we use measure what we call an amplitude, not a power. And if we can make this sensitivity twice as good as it presently is, it means we see twice as far out into the universe. that's a big gain because the volume of the universe goes as the distance out cubed. And so if we can improve the detector a factor of 2, we get a factor of 8 more events. So there's a big premium in us making the experiment much more sensitive than it is now. And we spend a lot of our effort doing that. There's nothing about the present system that's ultimately limited. I think over what you'll see over the next 5 to 10 years is continual improvement where we have lots more examples of gravitational waves. Those will be used in 2 different ways. One is to see maybe other forms of gravitational waves than we've seen so far. And secondly, to understand what we've seen better. We don't know, for example, what the origin is of these black holes that we see, these binary black holes. And in fact, there's 2 or 3 different possible explanations of those. To distinguish those, we need good data and better data to do that. So.
Yeah.
Looking at all those people around me, I think I have to go a few decades back. During my student years, I happened to be in a lecture where Werner Heisenberg was the speaker invited. Well, I don't remember a lot of things. To be honest, I remember almost nothing, except that he spoke English in a very strong German accent. Well, one statement I remember, he said that scientists at his time were very close to the ideas of Einstein, and that if there was no Einstein existing, they would put forward some similar theory. Do you share this opinion?
Sure.
Thank you.
There's one here.
Thank you. Can you give us a feeling of how it is to run these experiments? Are you monitoring daily for very long periods, or are you?
Yeah. So the question is, how do you conduct such an experiment? And let me just say a couple things. If you work on an experiment, say at CERN, there you control everything, meaning that you decide what particles you have, you collide them together, and you study what happens, and you know exactly when to look for what. We don't have that luxury. It turns out that we don't have the ability to generate gravitational wave events ourselves. And not knowing how to do that, what we have to do is just have them generated in nature and find them, which means we have a much harder problem. We have to be available to gravitational waves, not knowing which ones or where at all times as much as we can, and be able to then select them out. And that's an awkward and difficult problem in experimental physics compared to one. When I grew up as an experimentalist, the first thing I learned is how important it is to control everything yourself. That's how you keep from getting wrong answers. And that wasn't possible, or is not now, for gravitational waves because we can't make a strong enough source. Luckily for us, the sources nature provides are so interesting that even though we can't do it all ourselves, we're learning a lot. But it makes the problem of doing the experiments very difficult. We have to be observing, kind of like astronomers do, but in a way that isn't as selective, looking here or there in the sky. I think there was one down here. So.
Yeah, one more question.
I really enjoyed this. My question was, is the signal so weak because it's inherently very weak, or is it because it's on top of a background that is hard to?
Yeah, So the question, when I talk about this very weak signal that's hard to measure, is it really that the signal is so weak, or is it just hard to pull it out from backgrounds? And there's a little bit of both here, which I'll say that basically that it is incredibly weak, and that's why I use these numbers that I did. The effect is just an incredibly small effect. But once you get such a small effect, then there is a lot of backgrounds that you have to deal with. So what limits us is our ability to handle those backgrounds in the instrument itself. The ones I showed, for example, were the shaking of the Earth. If the Earth shakes, and when it shakes, it basically moves around the mirrors that we have, and we can't measure things as accurately. There's just environmental things. A truck runs down the road near us, or you asked about space. Okay. One thing you might say is things should be better in space. Of course, it's harder to do a sophisticated experiment in space, but space provides us with two things. One is that it enables us to look at gravitational waves in a different regime. The ones we look at on the Earth are where we're able on the Earth to actually do experimentation. That turns out to be the audio band. We've learned to communicate with each other because that's where it's quietest on the Earth. So we work from what we call 10 hertz to 10,000 hertz. If we go into space, then, which they're doing, then you work in a different frequency regime. And that's very much like astronomy. So astronomy, we now put up the wonderful new telescope, and it's working in the infrared instead of the visible. And we've worked in the ultraviolet and radio and so forth and so on. So in gravitational waves, you want to work at all the different frequencies. And so the main thing that space does is not make it quieter, but make kind of an alternate regime of frequencies that aren't accessible on the Earth's surface. And the experiment is called LISA. It's funded by the European Space Agency, and the American NASA is a minor partner. And we had a talk on it this morning here for the students, and it's scheduled to be in space in about the mid-2030s.
I have to thank our speaker again and again. There is a reception outside for all of us. Please come.